you want to title your notes or whatever you're taking on this, you can title it The Introduction to Geometry. We're going to talk about what geometry is, where it came from, people involved in it, different types of geometry. Some of this you're going to see on test. I'll try to mention those things. You're going to see some vocabulary here that you can fill out and use on your vocabulary list that you make. There'll be several things. Basically, by the time you get through this, you'll know the very basics of geometry, the terms that we're going to use, how we build geometric proofs, and some of the things that we're going to be doing all year long. Basically, there's one man who's really involved in geometry all the way along. His name is Euclid. Let's get that written down. E-U-C-L-I-D. Euclid. He was a Greek, and he lived in the 300 BC area. So you're talking about 2,300 years ago. Around 300 BC, he wrote a book. It's called Euclid's Elements. It is basically a mathematics book, and it also describes the geometry that we use. In it, he named 5 postulates or assumptions on which he bases his geometry, which we call Euclidean geometry. And Euclidean geometry is based on 5 postulates. Now, a postulate is an assumption. It is a statement or an assumption based on observations that is assumed to be true, accepted as true, and does not need to be proven. Okay? Let me say that one more time. A postulate is a statement or an assumption that is accepted as true, that does not need to be proven. Okay? Sometimes also we use the term axiom. Very similar. You can use those all 3 together. Postulate, assumption, and axiom, basically for what we're going to talk about, all mean the same thing. Now, the first postulate that Euclid came up with was, or he stated, was that, we can draw a straight line between 2 points. Or 2 points define a line. Okay? The second postulate that he stated was, once we have a line, we can extend that line by simply continuing to draw a straight line. We can extend a straight line by continuing with a straight line. Pretty simple stuff. The third one was, we can define a circle by describing a center and a distance or a radius. Circle defined by a center and a radius. Okay? The fourth one is pretty simple. All right angles are equal to each other. Okay? So these are the first 4 of his postulates or assumptions. 2 points define a line. Simply that. We can draw a line from one point to any other point, or from any point to any other point. Number 2, we can extend that straight line by continuing with a straight line. In other words, just simply continuing that line with a straight line, and it can go on forever in both directions. Number 3, we can define a circle by describing a center and a radius. And that's what defines a circle. Number 4, all right angles are equal to each other. Those are the first four of his postulates. Now we're going to start over with the fifth one because it's very important. Remember Euclid, about 300 BC, wrote a book called Euclid's Elements, and in it he described what we now call Euclidean geometry. Euclidean geometry, which is what we're going to be studying this year. Okay? First four postulates we just stated. Now we're going to work on his fifth. Why? Because his fifth is the one that everybody started challenging right from the beginning. However, no serious challenges were mounted until the 19th century. Believe that 1900 years passed before there was a serious challenge. The fifth one is called the parallel postulate. You will see this term again, and you need to be able to relate it to the fifth postulate is the parallel postulate. Okay, the parallel postulate, I'm going to draw a picture and then we're going to describe it. Parallel postulate says that if I have two lines and I intersect them with another line such that the line that intersects them creates right angles with both of those lines, then those two lines are parallel or never meet. Okay? Now that's a rewording of the parallel postulate. In all actuality, what Euclid said was this. If I have two lines that are like that, and I intersect them with another line such that the interior angles on one side of the line, let's take this angle 1 and let's say this angle 2, if those two angles added together are less than two right angles, then the two lines that this other line intersects somewhere on this same side, somewhere, they will intersect. Okay? They will meet and they will intersect. State it one more time. If two lines are intersected by a third line in such a way that on one side of where the third line intersects on the interior angles, those two angles added together are less than two right angles added together, then those two lines will intersect on that line. Now we can extend that by simply saying if this angle, angle 1 and angle 2 are right angles, then those two lines will never intersect. Okay? You can further say that if those two angles, let's call them 3 and 4, when I add them together, if they're larger than two right angles, then they will never meet. Okay? The way we illustrate it is like this. Okay? Draws it like this. Now, several people started looking at that saying, well, we can think of examples where that's not true. And they would state them, so forth and so on, but there was no serious challenge until the 19th century. Okay? So let's go see what the challenge was to the parallel postulate of Euclidean geometry. Okay? So if we were to put a summary of the parallel postulate up here, okay? Parallel postulate. And in the middle, we're going to put how Euclidean geometry looks at it. Draw a little picture of it. Okay, we'll put a box around that. By the way, Euclidean geometry is the main geometry everybody uses. It works in our space. Everything is accepted as being true. It all works. Been using it for thousands of years. Now, the little picture we're going to use looks like this. We have two straight lines intersected by a third line. in such a way that the third line makes right angles with both of those. And the two lines that the third line intersects never meet. Now there is another type of geometry. We're going to call it elliptic. Didn't look too good there. Elliptic geometry. Okay? Now, the picture that we would draw of it for the parallel postulate looks like this. If we have two lines, because elliptic geometry looks like this, we can intersect those two lines at points with a third line where it is perpendicular. The third line is perpendicular to those two lines, and those lines are always going to meet. Okay? In our honors classes, we'll get into that a little bit later on in the year so you can see what it is. But basically what we're dealing with, we're no longer dealing with straight lines, we're dealing with curved lines, or curved lines that always meet somewhere. But at some point, we can intersect them with a line that is perpendicular at that point with those two lines. Okay? We're not going to use this. People use it for multiple things. Use it for spheres like the Earth, those kinds of things. Now the other one, geometry, that we have is called hyperbolic geometry. And you'll see these terms on tests or whatever else that people have, and you'll see some of the assumptions that they have, and they'll make those assumptions, they'll state the assumptions, and then want you to pick the best example of what those assumptions mean. Now, if Euclidean geometry says these two lines never meet, and they're straight, elliptic geometry means they act like an ellipse, or it's always going to meet. What do you think hyperbolic geometry says? Opposite of elliptic, they never meet. So basically, we have two lines that look like this when we intersect them with a third line in such a way that at the point of intersection of both of those lines, the third line is perpendicular or creates right angles. Then basically hyperbolic geometry says those lines will never meet. And they never touch. And on top of that, there's several lines that go through those points that will never meet and never touch. So what you see is basically elliptic geometry comes back and says, sorry Euclid, we don't agree with this. There's not just one set of lines here, and all the lines that go through those points are always going to touch because they all bend together. Okay? Now, hyperbolic geometry says the other, says, sorry Euclid, there's not just one set of lines that would be parallel there. There are multiple that and would never touch. There are multiple sets of lines that would never touch because we could simply come up here and describe another set that went through the very same point like that, and another one that came through like so, and so forth, and we could describe multiples of them. Okay? So this is the main challenge that the parallel postulate has had. The fifth postulate of Euclidean geometry. Okay, and the challenges are elliptic, hyperbolic, and there's many others. However, major challenge, first, major challenge appeared 1900. Okay, AD. All right? Euclid was born in 300 BC. He wrote his book 300 BC in that neighborhood. So it was like 2,000, 2,200 years before there was a major challenge to parallel postulate, the fifth postulate of Euclidean geometry. Now, go over these because you're going to see them on a test. Not necessarily elliptic in all those concepts, not necessarily hyperbolic, but basically you're going to be seeing those terms. All right? Now, we're going to clear the board and start talking about the building blocks of Euclidean geometry. Okay, we talked about postulates, and postulates are assumptions or statements that are accepted as true, that do not require any proof. So I'm going to build a building. In order to build a building, we have to have a foundation. So we're going to start with a foundation. The foundation of Euclidean geometry is what we call undefined terms. What in the world is undefined terms? Undefined terms are terms that we do not have a definition for like we normally think about a definition. Okay? They're terms that we have to use a description for or an example of. All right? And we'll get into what those are later in another lecture, and we'll talk about those. But basically, the very building blocks, very bare bones basis of our geometric system is what we call undefined terms. Now, from those undefined terms, we can make definitions and use definitions, okay, or create definitions. And from these, then we can build assumptions. Remember we said postulates or assumptions? Postulates, okay, that do not have to be proven. Postulates do not have to be proven. Then, from all of these, we can begin to build theorems. Theorems. Now, theorems are statements based upon undefined terms, definitions, and postulates and other theorems that require proof. Proof. Postulates do not require proof. Okay? The other thing that we can build our geometric system on is a close relative to a theorem. It's closely related to the same topics. It's close related or a very small addition to that theorem. And what we call those, corollaries. Okay? And corollaries basically follow the same rules as theorems. Corollaries have to be proven. Again, have to be proven. And what can you use to prove corollaries? Any and all of this. What can you use to prove theorems? You can use undefined terms, definitions, postulates, and theorems to prove theorems. Okay? And corollaries from other theorems. These two are tied together. You won't have a corollary unless you have a theorem. Corollary is an additional piece to that theorem that explains it a little further or is a reasonable extension of that. Now, let's review what we've gone over. Where our geometry came from, the man that we get it all from that we're going to study about is Euclid. Euclid was a Greek mathematician back in around 300 BC. Okay? He wrote a book called Euclid's Elements, and in it he described all kinds of math rules, axioms, assumptions, postulates, and in those he also described what we considered to be the definition of Euclidean geometry. 5 postulates. First postulate was we can draw a line from any point to any other point. Definition of a line. Straight line. 2 points to find a line. The second postulate was we can extend that line by simply continuing to draw a straight line as far as we want in either direction, both directions. Okay? The third postulate was we can define and describe a circle by identifying a center and a distance we call the radius, and that allows us to draw a circle. The fourth one, very simply said, all right angles are equal to each other. And then the big one and last one that had lots of challenges was called the parallel postulate, basically stating in Euclidean geometry straight lines that are intersected by a third line, and that third line forms right angles with those first 2 lines. Those 2 lines are parallel and never touch, but they're straight. From that, Several people took exception and said, wait a minute, we see space a little differently. One of those that came out was called elliptic. In other words, all lines bend and they come together, geometry. Another one was called hyperbolic. There's several multitudes of geometric systems. Those are two of the most well-known that challenge. Those challenges were not serious until the 19th century. And those challenges revolve around Euclid's fifth postulate, called the parallel postulate. Now, Euclidean geometry is based upon, and the basic building blocks are undefined terms at the bottom. That's why I put it down here, undefined terms. Then, based upon those undefined terms, we can begin to build definitions. Okay? Words, concepts we want to use. From the undefined terms and definitions, we can make statements or postulates. They are assumptions or statements that are accepted as true, do not require proof. We don't have to prove them. They're accepted as true. Then we can begin to build theorems. Theorems are statements that require proof. How do you prove them? You have to say where they came from. They came from undefined terms. These are accepted. Definitions and postulates or other theorems that have already been proven. And there are also corollaries. Corollaries are simple additions to theorems, reasonable extensions of a theorem that are along the same lines of that theorem, just an add-on phrase, reasonable extension of that. And corollaries also have to be proven. It can be proven using all these. Okay? These are the building blocks we're going to use in order to build our geometric system and to study geometry this year. Okay? Use this lecture, whatever, to fill in your vocabulary, make your vocabulary, as well as fill in the blanks that you've got on the sheet of paper there. And have any questions, please let me know. We will discuss this in class.